The remix, baby!
Action.
Hey, look, I have my phone on during school.
What is that? Well, Evan, you see, I'm playing with my magnetic levitator.
Pretty fascinating, huh, Evan? This is a closer look at our magnetic levitator. It is suspended in mid-air by magnetic technology. It can perpetually rotate 20 minutes with one twist. It is able to function by using magnetic forces offset from each other to float, but it needs the piece of plastic to hold it from flying out sideways.
Man, I bet there's nothing as cool as that.
Well, just wait till you see what I got.
Alright, so before Halsey gets into his demonstration, I just wanted to give a little explanation on diamagnetism. So we are perhaps all familiar with the wide range of experiments which can be used to demonstrate magnetism. Usually these show ferromagnetism or electromagnetism, but when it comes to demonstrations, their often overlooked cousin is diamagnetism. A diamagnetic material creates a magnetic field which opposes, at least to some extent, any external magnetic field the material is subject to. Diamagnetism is an effect arising from the change in orbital velocity of the electrons around the nucleus of the atom in response to an applied magnetic field. All materials show this diamagnetic response to an applied field, although, because this is a weak effect, it is overpowered in those materials which also exhibit ferromagnetism or paramagnetism. Common materials such as water, organic compounds such as wood, plastics, and metals, copper, gold, mercury, bismuth, are all diamagnetic, but only very slightly. This ability to repel magnetic fields gives us the possibility of being able to levitate objects. This has led to some interesting demonstrations such as the levitation of a live frog and the diamagnetically stabilized levitation of a permanent magnet between human fingers. These are spectacular demonstrations, but can only be achieved in the presence of an extremely large external magnetic field of around 10 Tesla, around 100,000 times greater than the Earth's magnetic field. Unfortunately, this prevents them from being shown in the classroom, but images and videos can be found online which make exciting viewing. Diamagnetism can be demonstrated in the classroom using permanent magnets and a small square of the best diamagnet at room temperature, pyrolytic graphite. This grows very slowly by a process called chemical vapor deposition, creating a highly ordered material where the carbon atoms form a layered hexagonal structure. Because of the low density of pyrolytic graphite, a thin sheet will be repelled by a sufficiently strong neodymium magnet. A thick piece will be too heavy, as the material above, about 0.5 millimeter, does not contribute much to the lift. If the piece is thin enough, it will simply slide right off the side of a single magnet, and refuse to sit still on it. To get a piece of pyrolytic graphite to sit still above a magnet, we need to find a way to force it to the center of a magnet. This can be achieved by using a set of 4 magnets, creating a magnetic potential well. The pole of each of the magnets, where the field is strongest, forces the graphite to the center. This effectively pins the graphite above the magnets. I will now show a diagram to demonstrate this experiment. This shows the magnets colored in red and blue, with their north and south poles arranged as shown, and the pyrolytic graphite in gray in the center. Note that the graphite sheet needs to be cleaved and cut slightly smaller than the size of a magnet. This creates a stable room temperature levitation demonstration where the graphite is levitated at about 1 millimeter above the magnets. When pushed gently down, the graphite moves, but if pressure is removed, it levitates again. Take it away, Halsey.
So as you can see here, we have 4 neodymium magnets that have a pretty strong magnetic force, and then also 1 piece of graphite. And when we take the piece of graphite and put it over the magnets, it levitates a little bit. As you can see, when I shake it, it'll sort of move around.
Man, I bet there's no real-world application for this stuff.
You're wrong.
There is indeed real-world application for magnetic levitation. Practical applications of levitation include frictionless bearings for use in industry and levitating trains. The fastest train in the world is currently the JR Maglev in Yamanashi, Japan, which levitates using the repulsive force generated when large currents flow through superconducting coils of wire. It has reached a top speed of 581 kilometers per hour. I will now show a video explaining how maglev trains work.
Here in Germany, engineers are testing an experimental train that all but eliminates track friction. Because the train doesn't ride on tracks. This train literally floats on a magnetic field. It's called Maglev, for magnetic levitation.
Maglev technology is doing what a typical train does, except using electromagnets. Instead of having wheels and rails, we have magnets to lift and guide the vehicle, and then a non-contact propulsion system to propel the vehicle down the track.
With a powerful enough magnet, literally anything on Earth will levitate. A drop of water, an ice cube, even a strawberry. Maglev trains work like this. When the system is first powered on, a powerful electromagnetic field lifts the train up, about an inch off the track. Powerful generators in the track then begin to produce waves of magnetic energy, which propel the train forward. Because the train never makes physical contact with the guideway, there's no friction. And that makes the train very fast. The current model is designed to go as fast as 310 miles per hour. But the technology can potentially go much faster.
Well, I guess magnetic levitation is pretty cool.
Yes, it is.